Anyway, good morning, everybody. Yeah, regular expressions, they're not known to be particularly easy, but it is possible for regular expressions to be relatively simple. So we've got one here that's got an anchor that matches the beginning of a line, a dot that matches any character, and then a B and a C. And it's not too difficult to see if this matches an input string. So quickly raise your hand if you think this matches. We got some hands that went up. Yeah, and it does match. Some of you couldn't be bothered, but that I understand. So there is indeed some character followed by a B and a C at the beginning of the string here. But it doesn't take much to make it a lot more difficult to do that in our heads. So raise your hand if you think this one matches. Raise your hand if you think it doesn't match. And we'll just raise your hand if you just can't be bothered to even look at this. Yeah, okay, that works. There were a couple hands that went up at the beginning. It does, in fact, match, but that's not, yeah, it's not really the point. There's a few things that make this one a lot more difficult to run in our heads. For one thing, this pattern is a lot harder to visually parse than the last one. There's a bunch of syntax crammed into a small space here. But the pattern also represents a surprisingly complex process. We've got a nested subexpression. There's looping in here. There's conditional logic in here. There's this possibility for backtracking, which requires keeping track of multiple possible paths at once. So there's a lot going on here. So rather than try and do this in our heads, we're going to talk today about how the Ruby regular expression engine actually does it. And just to be specific, when I say Ruby here, I'm talking about C Ruby in particular. And the engine that I'm talking about is really the regular expression implementation in the C Ruby code base, which was originally based on a fork of another engine called Oniguruma. So we're going to read through some of the real code of this Ruby regular expression engine and see how it works. Reading through the code of a regular expression engine is not the only way to understand how regular expressions work. There's lots of other ways to visualize and reason about them. There's all kinds of theory. Maybe you've seen some graphs that look something like that. All that is really useful stuff, but it's just not what we're going to talk about today. I found that by looking under the hood of this engine, if you'll allow me that one, and realizing that it's something that we can read and understand has helped kind of solidify my understanding of regular expressions. It's made the concepts more concrete. It's helped demystify them a bit. So hopefully some of the stuff we talk about today will do that for you as well. Basically, during this talk, I'm going to try and convince you that this is a reasonable and helpful way to think about this regular expression. So, but I should probably backtrack a little. So, so one person laughed at me saying backtrack, so thanks for that as well. Currently, this is just a string of characters. In order for the regular expression engine to match this against some input, it's going to need to treat this as a program that it can run. To do that, it first needs to parse that program into some kind of data structure it can work with. That'll be an AST, or an abstract syntax tree. It's then going to compile that into bytecode, and we'll talk more later about what this bytecode actually is. And then finally, to see if some input matches, it's going to run that bytecode on a small virtual machine, or a VM. And that sounds fancier than it is. We're going to see some of the code for that later. And this here is really the outline for the rest of the talk, the parse, compile, execute. If I take away the regular expression-specific bits, this outline might look familiar to some of you. And that's because these are standard steps that could apply to any number of programming languages, including Ruby itself. I think I've maybe seen a talk about how this works in Ruby. But that's actually kind of part of what's neat about exploring this regular expression engine. The primary goal here today is to understand how regular expressions work better, but it also offers this nice kind of practical introduction to general concepts. You get to see how things work in a real code base, but it's one that's small enough to make some sense of in a reasonable amount of time. It's mainly in these 3 conveniently named files. So for the rest of the talk, we're going to look into some of how this works. We're going to dig into the code a little bit. First up, parsing. So the goal here is going to be to turn this string of characters into a structured tree. And this is going to be a two-step process. The first step is to turn this into tokens. And this is kind of like arranging characters in letters into words before putting them into sentences. So the tokens here, there's an anchor token for the caret, an anychar token for the dot, and then 2 string tokens for the B and the C. And you see there's a one-to-one correspondence here. This is often the case with regular expressions because so much of the syntax is these single letter things, single character things. That's part of what makes regular expressions hard to read, but it makes them pretty easy to tokenize. And then next, these tokens are used to build AST nodes. So the anchor token will get transformed into an anchor node, anychar into an any node, and then the 2 string tokens will end up as part of this 1 string node. So I'm going to show you a little bit of the code responsible for these translations, but not really because it's particularly interesting, actually kind of the opposite. It's like kind of boring and simple. So when the parser needs a token, it's going to call this function fetch token. It's mainly a switch statement on individual characters. So there's a case for the caret, a case for the dot here. And then it will create tokens of the corresponding type. So the caret becomes an anchor token, dot becomes an anychar token. And then some of the tokens also have some additional information. Like there's many different kinds of anchors. This one is specifically the begin line anchor. And then anything that doesn't match one of the special characters in the switch statement is treated as a string token. The tokens are then used to build nodes for the tree, and the main function that's doing most of the work there is this parseExp function. And just like fetch token, it's basically a big switch statement. Just this time it's switching on the token types instead of on the characters. For the anchor token, it builds a new anchor node by calling this node new anchor function and passing the subtype as an argument. For the anychar token, it builds an anychar node. And just in case you're put off by this being C code, if we rewrote this in Ruby, it would look virtually the same. Just in Ruby, we'd be instantiating Ruby objects, whereas in the C code, we're calling these functions that allocate structs and set properties on them. Handling the string token is just a little bit more complicated. It starts out the same way, builds a new string node, but then it loops around and continues fetching more tokens, and as long as it keeps seeing string tokens, it will concatenate them onto that existing node instead of creating a separate node for every character. So that's all the parsing code I'm really going to show. It's only a little small piece of the parsing, but that's kind of the core of it. It's mostly just a couple of switch statements translating the characters in the pattern into these nodes. And all that's left now is to connect them together to form some kind of tree. And they have to be connected in a way that preserves their order from left to right. And so that's done with this linked list. And this is now the complete abstract syntax tree for this particular pattern. If it doesn't look like a tree, you can turn your head to the side a little bit. That first list node is the root of the tree. In a way, this is not really that interesting. We were able to parse this same regular expression in our heads. This maybe kind of matches how we did that. There's 3 separate things in order. It gets a little bit more interesting with this more complicated pattern. The tree is going to capture some of that complexity, but I think it does it in a way that's helpful to see. So I'm going to show the overall structure of this one, but not with all the code. So first of all, this pattern has 2 branches. They'll get connected in the tree with this alt node. When visually parsing this pattern, it's kind of easy to miss that branching. There's that or H hiding out there at the end. It's also easy to get the precedence wrong. You might think it's G or H rather than entire left-hand side or H. It's a common mistake. But in the tree, the branching is very clear as this alt node with 2 alternative paths coming out of it. And this reveals one of the things that makes this pattern more complex than the last one. There's more than one possibility here. And at runtime, the engine may have to explore both of those paths to find a match. If we zoom in now into the branch on the left, this one is kind of similar in some ways to the simpler pattern that we started with. It's basically an ordered list of things. all of these will get parsed by that parse X switch statement that we saw, and then they get connected together in order with these list nodes. But one of these expressions has a lot more going on than the others. So a whole bunch of characters in here. First of all, I say first of all, but actually it's last of all, is the plus, which is the quantifier that's hanging out at the end there. It's not always obvious what a quantifier applies to exactly when you're just looking at the regular expression. In this case, the plus is applying to everything in the parentheses. But in the tree, I think it's a little easier to see. It's a quantifier node that's wrapping, it's the parent node of whatever it applies to. Then we've got parentheses, and inside of the parentheses is a nested subexpression. So this is a complete pattern that's following the same parsing rules as the outer pattern, and it produces a subtree within the larger tree. It's basically like a little regular expression inside of the larger regular expression. And actually, this would be a valid regular expression on its own as well. So if I put all that together without showing too many of the specifics, the overall structure of this tree looks like this. This is too much stuff for one slide, so sorry about that. But at the top, there's this alt node with the 2 branches coming out of it. The left branch is a long list of things, and then one of the items in that list is itself a list of things wrapped by this quantifier node. So, I don't know. I find it really helpful to visualize regular expressions like this. It's a structured tree rather than this cryptic string of characters. And I find myself kind of doing this in my head now, not necessarily writing it out, but thinking about it like this, thinking like the parser would think, I guess. And once you can kind of visualize the structure, it gets a lot easier to reason about what the pattern is actually doing, what it's specifying. So that's parsing, translates the pattern into a structured tree. Things could stop here. It's possible to run a program by walking through the tree and running some code along the way. Some of you may know that that's how early versions of Ruby worked. But it turns out there's a faster way to run things, which is to compile that tree into bytecode. This compilation step will essentially flatten the tree out into some continuous bytes in memory. And what we end up with looks like this. It's a sequence of bytes represented here as hex values. But they're not just any bytes. This is now an executable program that the virtual machine is going to understand and be able to run. In order for us to understand them, I should probably put some human readable names next to them because staring at a bunch of bytes is terrible. So byte 2A is the begin line opcode. And an opcode is basically an instruction for the virtual machine, and it's going to correspond to some code that the VM will run when it sees that instruction. So when the VM sees this byte 2A, it's going to execute some code that checks whether it's at the beginning of a line. Byte 16 is the anychar opcode. Byte 03 is the exact2 opcode, which also takes an operand, which you can think of as like an argument. So that the hex 62 and 63 in the bytecode there are really just lowercase b and c. And then finally, 01 is the end instruction. So that's the bytecode we're going to end up with for this regular expression. And the way we're going to get there is by compiling this tree into that bytecode using a function called compile tree. And yeah, it's another switch statement. So we're just like going from one format to another with a bunch of switch statements. This time we're switching on the node type. The list node is kind of the easiest to handle because the list node doesn't actually really have any information. It's just a way to put things in order. So you don't need to look too closely at this. This is just walking through every item in the linked list and then calling compile tree for each item. The next one is the anchor. So the anchor node, there's various kinds of anchors. So there's another switch statement in there. For the begin line case, here's the code. Here's what does the translation. So this adds the begin line opcode into this buffer of compiled bytecode. So it's writing 1 byte into memory somewhere. The opcodes do have human readable names in the code. So this op begin line is the opcode that we're writing. But ultimately, that's just a name for a number. It's an enum value, so op begin line is just the number 42. And that's what shows up in the compiled bytecode. Hex 2A is just 42. Same deal for the any node. It adds this any char opcode, which is hex 16, into the compiled bytecode. Strings are slightly more complicated because there's some specialized opcodes for strings of different lengths. And this sort of specialization is really common. There's way more opcodes than there are node types. And a lot of these are for performance optimizations. So in this case, we select 03, which is the exact to instruction. Some opcodes also require a length to be written into the bytecode, but exact2 doesn't because it's always going to be a string of length 2. And then finally, it writes the bytes of the string into the bytecode. So that hex 62 and hex 63 are the lowercase b and c from the pattern. Question? Yeah, why not? Yeah, that just gets tacked on at the end. So like it calls compile tree, and then at the very end, it tacks on a 01. So that end instruction is always there. Nice, nice catch. Wow, I thought nobody would notice that I just like didn't put that there. That's you're really paying attention. I love that. Where was I? Yeah. So we started with the sequence of characters. We watched the engine parse that into a structured tree, and then it compiled it into a sequence of bytes. So we've just like changed the format around a little bit so far. Now we get to the exciting part, which is that these bytes are now an executable program, and we can run them through the virtual machine. So what we really want to do here is see if this string matches this pattern. We already know it does because we did it in our heads at the beginning of the talk. So we're finally going to see the virtual machine. This is it, the great reveal. It's another switch statement, basically. If you want to know why I said basically, you can ask me later. But yeah, this is pretty much it. There's a function called matchat, and it runs what's called the VM loop. It's a switch statement that runs in a loop, and it processes each instruction in the bytecode as it goes. And so the switch statement will have a case for each of these opcodes. The easiest way to explain it is really to watch it run, so that's what we're going to do. I've got the bytecode here on the left. I've got the input string we want to match against on the right. There's some state stored in these variables, p pointing right now at the beginning of the bytecode, s starts out pointing at the beginning of the input string, and then we've got this switch statement that's running in a loop. The first instruction in the bytecode is 2a, which is the begin line opcode. So the switch statement is going to hit this begin line case. And then it also immediately increments p forward by 1. That's what the plus plus after the p is doing. And now here's the actual code for the begin line instruction. I feel like I cheated because there's this on begin line macro that does all the real work. But yeah, basically, if s is at the beginning of a line, it will break us out of the switch statement, which means it goes back to the top of this VM loop and enters the switch statement again. Otherwise, it goes to some code that handles match failures. S is at the beginning of a line here. It's all the way at the beginning of the string. And so it does that break thing, goes back to the top of the switch statement. But P is now on a new instruction. It's on 1.6, which is the anychar instruction. This one will first check that there's at least one character available in the input string. There's plenty of characters available after S. And if so, it will increment S forward by 1. And it doesn't particularly matter what S was pointing to there. This matches any character. It goes back to the top of the VM loop into the switch statement again. P is now on 03, which is the exact2 instruction. This one is going to check whether the character that P is pointing to matches the character that S is pointing to. Hex 62 is just another name for lowercase b. So P and S do match here, and it will increment P and S forward by 1. This is exact2, so it will then do the exact same thing again. Hex 63 is lowercase c. It matches the c that S is pointing to. It increments both P and S forward. And by the way, writing out the code explicitly like that is the optimization of exec2. Turns out it's faster to write the code out explicitly like that twice than to do loop. I think there's an exec 3 and 4 and 5 before it goes to exec n and loops. So an optimization for small strings, basically. And then at this point, it's on the last instruction, 0, 1, which is op-end. And if it reaches here, it means it's done and it matches. So that's that. We did it. We've now seen a simple regular expression get parsed and compiled and then executed on the virtual machine. I'll just take a breath now. I feel like, okay, I can relax. I want to walk through one more example that's a little bit more complicated than this one. Not too complicated, but it's deceptive. So we've got a /w here. That matches word characters. That's letters, numbers, and underscores. It's followed by a star quantifier, which means this pattern is going to match 0 or more of these word characters. And then there's the dot and the C. Some of this we already know. The dot and the C are instructions we've seen, basically. There's any char instruction. There's exact1, which is very similar to exact2, and then the end instruction. There's also a new instruction for matching a single one of these word characters. But the parts that I'm really interested in here are the remaining two, and they're both related to the star quantifier. So one of the instructions is a jump. This is how the virtual machine is going to do a loop. Since the instructions always will get executed in order, jumping backwards means it's going to keep executing the same ones over and over. So this is going to loop around and match as many of these word characters as possible. But the thing with the star is that it doesn't know how many characters it needs to match in order for the overall match to succeed. So we'll start looping through and greedily matching as many characters as it possibly can. But if that doesn't work, if there's no characters left for the dot and the C, it may need to backtrack at that point and go back and match fewer characters to produce an overall match. In order to do that backtracking, it has to remember all the places that it's been. And that's what this last instruction is. On every iteration through the loop, it's going to push some state onto a stack called the backtrack stack, which I think must have been named by Dr. Seuss, like backtrack stack. Anyway, this will allow the virtual machine to recover from match failures and try out some alternate path. And if that didn't click yet, that's fine. We're about to walk through this. Maybe you can already see that this will match doing the string ABC. But the path that the virtual machine takes to arrive at that is kind of interesting. So we'll walk through it. We start out here with the push instruction. This one gets an int as an operand. So that 06000000 is really just the number 6. There's some weird looking casting stuff. Don't worry about it, it's fine. It's just 6. Then it moves P forward past the int that it just read, getting ready to execute the next instruction. But before it executes the next instruction, it will do this stack push. That's pushing some state onto the backtrack stack. And specifically, it's pushing the current position in the input string, so that's S, which is pointing to the lowercase a, as well as the instruction that it should start with when it needs to backtrack. So that's P plus the relative address of 6. So P forward by 6 bytes is that 1/6 instruction, which is the any char instruction. So it's going to push those two positions of P and S onto the backtrack stack. And now if there's ever a match failure, it's going to be able to pop that back off the backtrack stack, reset P and S to those saved values, and continue on from there. We'll see that work in a second. After pushing the stack, it goes to the next instruction, which is this ASCII word instruction. This one works similarly to some that we've seen already. First, it ensures that there's a character available. If that character is not a word character, it will fail the match. If it is a word character, it will increment S forward by 1. So that's what happens. Now it's on the jump instruction. This one also gets an int operand. F5, FF is -11. This is a signed int. Again, don't worry about it. It's just -11. It's fine. Then it's going to move P around a little bit. So it moves it past the int that it just read, and then it will move it by that relative address that it calculated. So that's moving it by -11, so backwards 11 bytes, all the way back to the beginning of the bytecode. And now we're basically stuck in a loop. So we'll push to the stack again with S now at lowercase b. It gets to the word instruction again and increments S forward, gets to the jump again, goes all the way back. Pushes to the stack, gets to the word instruction and increments S, jumps all the way back. Should I keep going? Yeah, I'll keep going. It pushes to the stack again, but now actually something different happens. There's no more characters available. S is past the end of the string. And so this ASCII word instruction will fail. This data ensure check will fail. There's no characters. If there were no backtrack stack, it would be done at this point. The match would just fail. But because we have all these possibilities still that we can try out, the VM will now pop from the stack and reset P and S to those saved positions and continue on from there. So that's what's going to happen. P and S are going to move. Actually, S won't move. It's already at the end of the string. Here we go. Pop off the stack. We're now on the anychar instruction. So this has finally broken us out of that star quantifier loop. We're on the anychar for the first time. Unfortunately, there aren't any characters left to match. S is still past the end of the string. And so this will fail again, and the VM will pop off the stack yet again. That puts it back on the anychar instruction, but now S is pointing to lowercase c instead of pointing past the end of the string. This time there is a character available. I should probably do that again. There is a character available, so S will get incremented forward, and it moves on to the next instruction, which is exact 1. But now we're out of characters again, so this will fail. And it has to pop off the stack again. Back to the anychar instruction. S is pointing to lowercase b. That matches. It increments S forward. Gets to exact 1 again. This time, there is a character. S is pointing to lowercase c. P is pointing to hex 63, which is lowercase c. So it will increment both P and S forward. And we get to the end instruction, and sure enough, this does match. All right, that was a lot. Don't worry if you didn't follow along with everything. It's fine. The main thing here really is just that the jump instruction, together with this backtrack stack, allows for some pretty complicated control flow. It allows us to explore many different possible paths. I'm about to show you one thing that's worse, so it'll be quick. At the beginning of the talk, I sort of jokingly told you that this was reasonable and helpful. It turns out we can actually make some sense of this now. So these are all instructions that we saw today. They're handling like one individual expression within the pattern. There's one that we didn't talk about. Sorry, this was a cut. I just didn't have enough time. This is the character class. It's truncated quite a bit here because the operand is 32 bytes long, or really 256 bits long, where each bit represents a particular character that could be part of or not part of the character class. It's just a fun little detail that allows for constant time matching of characters in a character class. And then there's a bunch of pushes and pops. These are for the star and the plus quantifiers, as well as for the alt branching. And this right here is the main thing that makes this regular expression difficult to reason about in our heads. There's some really complicated control flow going on here. If you're looking carefully, I know some people are looking really carefully, thank you. There's a push if peak next here, which is just an optimization to avoid backtracking in cases where it will obviously fail. And that's what these next couple of instructions are about as well. There's a backtracking related optimization added in Ruby 3.2. When there's nested loops, regular expressions could run in exponential time, but this optimization lets them run in linear time instead. It's pretty cool. And then finally, there's a couple instructions that tell the engine when to start and stop capturing for a capture group. All right, this is way too much stuff to put on a slide. I'm so sorry. The point here is really that it's possible for us to see these instructions and to reason about how this regular expression actually executes. It's a program. So I hope that the next time you're working, yes, I got a laugh. I'm so happy. I hope that the next time you're working with regular expressions, you'll remember that they're not just cryptic patterns, they're programs. And just like any program, it's possible to reason about and understand how they work. Now, I'm not suggesting you have to go and read the source code for the regular expression engine every time you get confused. But it also doesn't need to be a total black box that you can't understand. If you do happen to decide to dive into the source code, you'll learn about more than just regular expressions. You're going to understand Ruby better too. If you enjoyed this, you might enjoy some of these as well. In particular, I need to highlight this first blog post by my colleague, Adam Hess, a GitHub colleague. It covers a bunch of the same content of this talk, and I think he might have given me the idea for this talk, and I just forgot, and then years later proposed it. So thank you, Adam, for the idea. He's not here, but it's fine. And yeah, thank you to all of you. Appreciate it.